Good morning, Cal. As you can tell, it's probably based on my outfit. I was literally ready about to head out the door, and then I got the text. So now I'm making this very early in the morning. So let's get ready. Today, you might be the only class I record for too, just because you guys are a little bit more important of a class to make sure that we're on track for. But essentially, I just wanted to go over a few examples from lesson 6 that we're about to start today. Highly recommend reading through it. Some of it looks rather straightforward, but there's a few of them I actually want to go through together as a class tomorrow. But today I at least want to introduce a few of the examples because they're kind of cool. And optimization is actually a very useful tactic beyond Calc 1. You guys can actually use this, and people use it all the time without even knowing. Right? And optimization, by definition, is being the most efficient and getting the most bang for the buck, essentially. So you want to optimize your profits. You want to optimize, like, or be as cost effective as possible, which we're actually going to see an example of in just a second. But I just wanted to walk through examples 1 and 4 from the notes. So let's get ready for example 1. Find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. Okay, so unit 5 has just been about if you couldn't pick up maxima and minima. So we have been using maximum to graph polynomial functions. Same thing with minima, and we've been using derivatives, right? When derivative equals 0, you have a max or a min. So let's do the example. So how do we set this up? Well, list two numbers. You don't know what there are, so call them x and y. So we got x being number 1 and y being the other number. So you got two of them. Perfect. And then being able to read math and write it down is the sum of the first number and the twice the second is equal to 64. And then their product is a maximum. So x times y is equal to max, which I have up there already, but I'm writing it down again just to get the idea. So your objective is to solve one of the equations and then substitute that in, just like we do for systems of equations, right? Solve for one, substitute it in, and then solve for it. So here, the best way to probably go about it is to take the one that's not a min or a max, so the one that you're not trying to optimize, and solve for one of the variables. Probably the easiest way to go about it is to solve for y. So let's solve for y. There's multiple ways you could do it, and you'll get the same answer regardless. So 2y equals 64 minus x, and then you got y is 32 minus x over 2. All right, perfect. So now you substitute this in for that y right here. So you got x, and instead of y, you got y, or 32 minus x over 2. And that equals max. So we don't know what the max is yet, but we'll get to that part in just a second. So now you distribute. So you got 32x minus x squared over 2 is equal to max. And now here's where the max part takes place. Now you want to take the derivative of this whole thing. Well, what do you mean take a derivative? With respect to what? There's no y equal. You can't find y prime or f prime. Well, yeah, but in general, you can take a derivative so long as you know what your derivative is with respect to. Now, we haven't gone with the notation. That's a little bit weirder and more wonky, but we will in a little bit. So now you want to take a derivative. So 32x turns into 32. Power rule it, so x squared over 2 cancels just x. And as you know, by this point, maxima and minima are when your derivative is equal to 0. So max just turns into 0 now because you're taking a derivative. So now x equals 32. Perfect. And now, in order to find what y is, use this equation that we solved y for already. So plugging it in, we got 32 minus 32 over 2. We found x already. So y is equal to 16. And there we go. Perfect. All right. So that's example 1 done. I know there's usually 2 questions I do here, as in your video for the Google form. The last one I'll do is going to be after this lesson, or after example 4. I honestly don't know what my first question is going to be. Usually I'll make the math question at the end, so let's see. Guess question 1 is, after this video, do you think we're going to need to push the test back to next week, or should we rip the end off and just do it this Friday? Because on this type of question, there's only one of them, and the other one's going to be a bonus on your test. In other words, how do you feel about 5.1 through 5.5? I know it's been AMI like no other business, but it's good to get an honest poll. So question 1 is, should we keep the test Friday or push it back to next week? And it'll have to be Monday or Tuesday. So we'll just have an extra day review if we push back. So answer that for Google form question 1. All right, question 2, or example number 4, is about the aluminum can. So here, we're trying to find the least amount of aluminum we can use that can hold a 40-inch or 40-inch cube volume. Now here's an actual really cool example, because engineers and factory workers use this all the time to try to maximize your profit, right? So, because aluminum can be pricey when you produce like millions of cans every day. So every little bit of square inch counts here. So how do you minimize the amount of aluminum you would need so you don't have that much surplus, with still being able to hold 40 or 8 fluid ounces or whatever that is? So really cool example. So and there are a few other examples we're going to go through together as a class, like skip number 2 and 3 for a reason, because I want to walk through number 2 in class and 3 in class as well. And then we'll walk through example number 6 in class as well, because those are just too important of an example to go through in a video, so without being confusing. So we're going to actually walk through those tomorrow together. Number 2, 3, and 4, or 2, 3, and 6. So example 4, let's knock out together. So the least amount of aluminum, meaning, because when you produce a can, it's the surface area technically. But you still want your volume to be 40. So, well, we got one of the numbers already. And here, how do you know the surface area of a volume, or the volume of a cylinder? Well, volume of a cylinder is just, if you think about it, just a circle stacked on top of each other. And that stack has got a height, and circles have a radius, so r. So if you think about it, it's just the area of the circle, pi r squared, and then just shoot it down with the height. Same thing with the surface area too. So surface area formula, if you don't know off the top of your head, just think about it intuitively. Surface area at the top is just pi r squared, which is where that comes from, the 2 pi r squared part. And then the pi r squared in the bottom, so adding those two together, pi r squared and pi r squared is 2 pi r squared. So that's that chunk, that's the surface area at the top and bottom. And then this part you've already known as well, because we did it last year in trig. It's just the circumference, which is 2 pi r. So it's the circumference, which is the perimeter of a circle, and you just shoot it down with the height. So yeah, that's all the surface area formula is, if you really think about it. But you're going to be provided any formula you might need, so don't worry about memorizing anything. All right, let's get back to the question. Volume's 40. All right, cool. And now we solve for one of the variables, just like we did before, and then we're going to substitute it in. So The easiest one to solve for is the one that has the least amount doing something with it. For example, pi r squared, we'd have to take a square root, and then when we take a derivative eventually, you'll have to do power real with 1/2 power, and that's just disgusting. So easiest way to go about it is to solve for h here. So 40 over pi r squared. All right, excellent. Plus, that's less substitution we have to do for the surface area formula. So now, let's plug it in to the surface area formula, substitute it in. The surface area is 2 pi r squared, and then plus 2 pi r, and then substitute this in for h. So 40 divided by pi r squared. All right. So before you take a derivative, let's clean it up a little bit. So surface area is 2 pi r squared. And then doing 2 times 40 is 80. So 80. And then here your pi's cancel. One of the r's cancel. So that just goes over r now. And now we can take a derivative. So let's see if that's legible. If not, then I'll switch back to green. Because we want to have the least, right? The minimum amount of surface area, which is why we take a derivative here. So when you take a derivative and you want to do least or greatest, set the derivative equal to 0. So surface area derivative is 0. So 0 equals. And then do the power rule here. So 2 pi r squared turns into 4 pi r. And then plus 80 divided by r. So this is r to the negative first power, if you think about it. So break it down, you got negative 80. And then r to the negative second. So that's just over r squared now. And now let's solve for r. So here, setting it equal to 0, probably solving the best way is to add the 80 over r squared over 4 pi r. Multiply your r over, so you got, and we'll do every step. I'm not going to skip any steps today. All right, divide by 4 divided by pi, so then you got 20 over pi equals r cubed, and then take a cube root. So r is equal to the cube root of 20 over pi. Punching that in your calculator, you'll get a value of about 1.85 inches. How precise do you need to be? Well, it depends on if you're actually using this or not in real life, right? Because you probably don't want to round up to 2, because at that point, then you're going to be losing millions of pounds of aluminum, but you probably don't want to be that precise to where if it's off by 1/1000th of an inch, then it's going to actually hurt your loss if you shut down the machine and try to recalibrate it to that very specific amount. Usually 9th or 10th or 1st or 2nd decimal place is good for general ideas. And of course, in order to find height, you punch that in to the height formula that we found way back when. So punch that in, you get your height to be about sorry, I couldn't find it on this little piece of paper. 3.71 inches. And there we go. And those would be your dimensions. And how do you know if it's a minimum or maximum? Well, you could do the sign check rule and plug in values for your derivative here. And see if it's going from minimum, so negative, to maximum at that very specific part. Okay. Now on the question 2 on your Google form, here's one of my favorite ones. It's going to be going over a little bit of physics. It's one of the most important physics formulas that you probably heard and memed about at some point. And it's the generalization of, because in calculus, we do a lot of physics, whether you like it or not, because that's how it's based off of. F equals MA. And they're vector equations, so technically, well, I know technically, you got your little vectors there, but that's not the actual formula for force. It's actually this, which is you've probably seen me wear the shirt already. Is the derivative with respect to time of momentum. Now, long story short, momentum is, and I'm gonna drop the vector sign, so if any physicist is watching this, I'm sorry, is just to get the point across. P, which is momentum, is mass times volume. So if we were to take a derivative of P, so P prime, then you can also take the derivative of MV, M prime, and V prime. And this is all with respect to time. So, and we'll go over related rates in Unit 4. So this is all with respect to time, meaning that time changes, you want to see the instantaneous rate of change with time. So P prime can actually be, and then you do the product rule here. So it's take derivative of the first, so M prime, leave the second alone, and then leave the first alone, take the derivative with respect to T with V. Now, V stands for velocity, M stands for mass. So here, if we remember, the derivative of velocity is, well, acceleration. And then this P prime is force. However, F equals MA, F equals something plus MA. What does this part do? Well, if you think about it from an actual physical standpoint, this is the instantaneous rate of change. Does mass ever change? Not really. Or does it? Is there a time where mass changes? And I can think of about 3 circumstances in real life where time or mass changes with time. Like as time goes on forward, because you can't go back in time, then your mass would change. Question 2 in your Google form is to think of a circumstance where that happens. So in other words, 99% of the time, M prime is equal to 0. So that usually just goes away. But your question on the Google form number 2 is, think of that 1% of the time where that doesn't happen. So where does M prime not equal 0 in real life? So think of a real life scenario where that's not equal to 0. Email me any questions. AMI. Yay.